Okay, so now we're going to talk about how we can statistically analyze data to find out if there are differences. Sometimes we want to see, and we're wondering if there are differences. Sometimes we're wondering if there are not differences. Can you think of those types of scenarios where we're wondering if there are differences?
What do you mean?
Well, like when would we perform an experiment to find out if there is more of something or less of something?
Oh, you mean like if we wanted to find out if there was more or less mercury in the water?
Very good, something like that. If we want to find out if here's a water sample over here that we think has no mercury, and then here's some that we're concerned that there is mercury, we want to see if there is more mercury in the other than in our sample compared to what were our standard, which we know has no mercury, right?
Okay.
Now, what about a scenario where we want to find out if we don't know if it's more or less, but if there's just a difference between one sample or the other?
When would we want to do that?
Well, how about this? How about if we have a test that tests for a toxin or something that we do not want in our sample, right? And the test is expensive, right? So we take samples and we send out 30 samples a day from our food production factory, and we're trying to make sure that the amount of a toxin isn't too high. But it costs $100 a sample, so we're spending $3,000 a day to test these samples, right? But then a bright, young analytical chemist comes in and says, look, you don't have to send these out. We can create a little tiny mini section of the lab here, run these samples. We can even run 50 a day and only do them for $1 each, right? We can really minimize the cost and do it ourselves. How's that sound?
Well, sounds good, but everybody would say, how do you know your test works?
That's right. That's right. And so we would want to have a way to statistically show that in the end, there's no difference between the new method's measurements and the old method's measurement, or the new technique, right?
Okay.
Very good. So we want to have a way to measure whether or not sometimes techniques are higher or lower, or if there's no difference. If we can show that there is a normal distribution of the samples by running lots of samples, right, then clearly we could show that there would be a difference, as shown here, between two normal distributions in A. And if we showed that there was no difference in the normal distributions, right, that would be B, right? So maybe A here is, here's our water sample, lower value. Here's our water sample, and here's our water sample with mercury. And the two distinct normal distributions would show us, yep, we did have mercury. If we ran the two samples and showed there was no mercury, then that's what we would kind of expect to see. If we ran our new method for testing for the toxin in the food, and we showed that we were comparing methods, and the methods that we sent out, the samples that we sent out, the normal distribution for those values came back compared to the samples that we did in-house, and we got the same value, then we would want to say it'd be a good idea to adopt the new sampling technique, right? However, if there was a difference there, then we would say that there is a determinant error somewhere in our method, and we have to fix that determinant error. In a sample like this, you're saying essentially that although there's a slight difference, that slight difference is likely due to an indeterminate error, or what we call a random error, one that you're not going to be able to find. It's indeterminate. You can't determine where it's coming from. But this is the tricky part, right? This is the tricky part where there's possibly a difference, but they're overlying each other. And so we need what's called a significance test, a test to determine whether there's significant differences between the two samples. And sometimes you're interested if it's favorable for you and the company if there isn't a difference. Sometimes it's favorable for the outcome if there is a difference, to teach you, let you learn information. You never want that to sway your decision. but it determines what kind of significant test you use, okay? And in this significant testing, we have two different tools. One we call the null hypothesis, and the other we call the alternative hypothesis. The null hypothesis is basically that the indeterminate errors are sufficient to explain the differences. Or in other words, these two differences are not significant. All right, the differences are not significant. And that's the null hypothesis. The alternative hypothesis is that the indeterminate errors cannot explain the difference, and the difference is due to the presence of something, or it's due to determinate errors. All right? Okay. Now, the difference between the null hypothesis and the alternative hypothesis, right, creates what we call an alpha number, And we have we use this alpha number as a confidence level. And our confidence intervals that we talked about before, divided by 100, so essentially turning our confidence interval into a fraction, 1 minus that value would equal our confidence value, or our p-value, some people call it, or alpha. All right. So in this textbook, we use alpha, but that's the same as p, essentially. And you're going to read a paper about p-values and what they mean. But essentially, the lower the p-value, the better, because as you see here, if this value here was the same, if your confidence interval was basically 100%, right? So 100 divided by 100 would be 1, and then 1 minus 1 would be 0. So the lower the alpha value, the lower the p-value, the easier it is to accept the null hypothesis. All right? So essentially you're saying there's no difference in the null hypothesis, okay? And the larger the value is above 0.05, now 0.05 is for a 95% confidence level, right? So if it's above 0.05, you can say that you are not 95% confident that you can keep the null hypothesis. You have to reject it and accept the alternative hypothesis. Again, the null hypothesis is that there's no difference between the two samples. The alternative hypothesis is that random error is not causing the difference. The difference is either determinate error or there's something different caused in the sample, right? Now, the 4 steps for a statistical analysis of data using any significance testing, right? You pose a question, right? And usually it's associated with the null hypothesis compared to the alternative hypothesis, right? And then you choose a confidence interval level for statistical analysis, and that's usually going to be 95%. And then you calculate the appropriate test statistic and compare it to some critical value. Okay? Now, most of what we're going to be doing, we're going to simplify for ourselves in Excel, and it will compare the value for us and report just an alpha value when we do a significance test. It'll result in an alpha value or a p-value. And so what we're looking for is that p-value being greater than or less than 0.05 for our 95% confidence level. Okay? And then we make the decision to either retain the null hypothesis or reject it, which is to say we accept the alternative hypothesis. Okay, so a one-tailed compared to a two-tailed significance test. And, you know, we're going to have lots of equations that we kind of have to look at in the next couple of sections here. But I'm less interested in us kind of memorizing them. We know where to go to get them. And if you become a statistician or somebody who really needs to dig deep, then you can use those equations. Equations differ from book to book, year to year, only slightly, but there can be variations. And so what's more probably useful to you is how to use this in Excel just to look at a set of data. And that's what we're going to That's going to be the take-home message. But you do need to make decisions when you use them about whether it's a one-tailed or a two-tailed test, for example. All right. And when you're referring to a one-tailed or a two-tailed test, what you're trying to see is the new, so here you have a normal distribution for your set of knowns, let's say, and then you are performing a sample. So you have your known and your unknown. If you have your known and you get this normal distribution, if your unknown shifts so that this space right here might be different, right? Or if it's on the other side, we call that a one-tailed test. This here, essentially what we're saying is your unknown is lower than your known, or you're expecting it, you're measuring, your question is it going to be lower or is it going to be the same? That's my question. In this scenario here, and both of these are one-tailed tests, is the value going to be higher or is it going to be the same? And that's your question. In a two-tailed test, what you're asking is the value going to be different? Is it going to be to the right or to the left? All right. Now, we had two examples that we talked about before. Do you remember our two examples?
Oh, you mean the mercury in the water and testing to see if your new method was good or not?
That's right. Which one of those do you think is a one-tailed test?
Well, the test where you are trying to do your laboratory stuff in-house, right? Where you're trying to see if your new method works.
Yeah.
That one, that might be wrong going higher, or it might be wrong going lower, right?
That's right.
So that would be like A down there.
Very good. And what kind of a tail test is that?
That's a two-tailed test.
Very good. So if it's going to be a problem, if it's wrong to the right or to the left, that's a two-tailed test, right? What about the mercury? What would that be?
Well, the mercury, you're expecting there to be more mercury in your sample, right? And if it shows there's less in your sample, that doesn't make any sense, right? So you're just measuring for if there is more. So that would be a one-tailed test.
Very good. You're measuring for if there's going to be more, so that's a one-tailed test. All right, excellent. Now, there are different types of errors. So that's what I want you to take home from here. How to know whether it's a one-tailed or a two-tailed test. Okay? And here's some more examples you can read about. Because a significant test relies on probability, there are still errors associated with the results. So for example, if alpha equals 0.05, which is your threshold, your cutoff, right? You would say if it's 0.05 exactly, then what?
Well, that means that's the minimum to be 95% confidence that the null hypothesis is rejected.
That's right. Rejected, meaning that there seems to be a difference. If this is higher, 0.06 or higher, anything higher than 0.05, then that would mean what in terms of your null hypothesis?
That you can't reject the null hypothesis. They might be the same.
That's right. Those concentrations might be the same. And again, that's not necessarily meaning that there is or isn't a toxin. It could be whether or not your new method is better or not than your old method, right?
Yeah.
Okay, so there's always that type of error, right? So even if it's at 0.05, that means there is a 5% probability that your choice to reject the null hypothesis was incorrect, right? So if you get this down to 0.00 or 0.001, for example, there's a 0.1% probability that your null hypothesis was actually unrejectable, right? So that is called type 1 error. And again, it's there. It's there. Just like we talked about before, you never want to say, this is the right value. You always want to kind of, at least in your statements, always provide some, in your mind, think about, I have this much confidence. I'm 99% sure that I saw that dog on the side of the road the other day, right? Something like that, because there's always a chance that you're incorrect. The second type of error is when we retain the null hypothesis even though it's false, okay? And this is a type 2 error, or a beta probability. And unfortunately, in most cases, we cannot calculate or estimate a value for beta, but the probability of type 2 error, however, is inversely proportional to the probability of type 1 error. So that means if type 1 error is very, very high, then type 2 error should be very low, and vice versa. If your type 1 error is, so in other words, if this value here is 0.005, then the likelihood of your type 2 error being high would be minimal. This would be low. Okay, very good. So, let's talk about how we would make some comparisons then. All right. And what it is we're doing always is we're looking at our calculated average, the average that we just calculated due to some set of experiments, to an actual average, right? To a real average on a population. Okay. And the confidence intervals that we can kind of compare, right? Here's our average with this constant confidence interval. We have what are called a t-statistic, a test statistic, or an expected, in this case, this is our average, right? Sorry, not our average, but our expected distribution. Remember how we had here, we could put in here our 95% confidence number, remember, which was our numbers of standard deviations, right? If we wanted to make sure we had a 95% confidence number. Do you remember that number in there?
Was that like the close to 2?
That's right, because if you contain 2, then you're just over 95%, 1.98 or something like that. That would be our expected value, our expected number of standard deviations, right? Well, if we have an expected test value there, we can look at our distributions in terms of these, again, test values on the lower end or the upper end, okay? And A, the shaded area under the normal distribution curve, shows the sample's confidence intervals for the actual average based on some expected error. Here in the solid bars, here in B and C, show the expected confidence interval explained by random error, given the choice of alpha and the available degrees of freedom. V. Now, do you remember what degrees of freedom were?
Degrees of freedom was like the number of measurements minus 1.
That's right. And here's our V, or our new symbol, V, for the degrees of freedom. So that's our variable we'll use later on. Okay? So essentially what we're talking about is that we have a table that has calculated possible t values for number or degrees of freedom. And here is our 95% confidence. And so we have, for the number of degrees of freedom, expected t values that we would be using. And again, we got to infinity here, and we get back to our 1.96, right? Which is the 95% confidence interval, right? Okay, so here is an example of how we can use a test to compare. Now this is known as a t-test, all right? And what we're doing is we're comparing this value to a table, a t-table, something in the table. So let's walk through this one together. We're determining the amount of sodium carbonate in a sample, and you want to check your procedure by analyzing a standard which says it's 98.76%. And then you do it 5 times, and the standard gave these 5 results. Using an alpha of 0.05, is there any evidence that your analysis is producing incorrect results? All right. So we take our mean and our standard deviation, and because there's no reason to believe that the results of the standard must be larger or smaller, we have to use a two-tailed test, right? Okay. then the null hypothesis is that basically the averages should be the same. So this should be the same as 98.76%. All right. And so the statistical t-test is to get our t-experimental, right, which is the difference between the two. So we can take the difference between this and our 98.7 here, 5 times the square root of our number of experiments, 5, and then dividing our standard deviation, or sorry, our standard deviation here. Okay. Now, I don't know why they put a 2 down here. I think that's supposed to be S for standard deviation, and our standard deviation is 0.0973. So we're seeing quite a few errors in here, but that's all right for an online book. And it's free, and they're gradually getting there. What we should do is we should collect all the errors and let them know so they can help fix them.
Yeah. I could do that.
You can do that?
Yeah.
Well, I could give you 2 extra credit points for every error that you find. How's that sound?
Oh, that sounds good.
Yeah, so you'd have to document the location of the error, the specific section, exactly where it's at. And then for every error that you find and document, and when I see them, I find them, and that's fine as long as you are documenting them for me. That would be great. And then we'll send that off to the publisher, and then they can fix that for us next semester.
Okay, sounds good.
All right, so there's another error you can document for your 2 points, 2 extra credit points. And I think we've seen like about 4 errors already in the book. So if you want to go back and find those, or if you remember where they're at. But moving forward, yeah, that's a good thing. Document those and send them to me, and I'll start recording your extra credit points. Okay? All right, so anyway, we get a value. This is our t expected value of 3.91. So again, we knew what the and we put our t expected in here, but then we rearranged it. We solved it for t expected, and that's the equation that we're using now, is solving for this t expected. So if we expect a t value of 3.91, and then we go to our appendix for a scenario where, so here's our appendix, and we can go to this appendix, but before we go, we want to look and remember that we're looking for 95% confidence interval where n equals 4. That's degrees of freedom equals 4. So here we go. Degrees of freedom is 4, 95% confidence. That's where we get our 2.776. Okay? So, where are we at? 2.776 or 2.78 is our value. And since our expected t value is greater, then we reject the null hypothesis. All right? So essentially, what we're saying is that we would have expected there to be a certain amount of deviation on our, on our sample measurement. We would have expected that certain amount of deviation, right? That's what this TXP, we always put a little bit of deviation, how much we would expect. And the amount that we would expect kind of is related to the number of samples we run, or our degrees of freedom. We ran 5 samples, but we had 4 degrees of freedom, right? And we can calculate what we would expect to see. We end up seeing that there's more of a difference. It's greater than 2.7. Therefore, it wasn't just indeterminate error. We never really know, like we said, but statistically, we would suggest that this was not just indeterminate error. It suggests that there is some sort of difference. Okay? So, let's read through this. Since TXP is greater than what we would expect, we reject the null hypothesis and accept the alternative hypothesis. At the 95% confidence level, the difference between these two is too large to be explained by indeterminate sources. Therefore, we have to go back and figure out why our test is not giving us the right value. Okay? All right, very good. So, how about to evaluate the accuracy of a new analytical method, an analyst determines the purity of a standard which is 100% and obtains the following values. Okay? Is there any evidence at 5% that there is a determinate error affecting the result? Okay, so let's give ourselves some space to work here a little bit. All right. What do we got to do?
Well, we got to find the standard deviation and the average.
Very good. So let's see if we can do that here. I'm going to copy this. Whoops. I'm just going to do Control C here. And then I'm going to bring in an Excel spreadsheet. Let's see, what did we find? We found that if we pasted them into Word first, I think it's just going to be easy enough for me to go like this. See how lazy I am?
I don't know. I think I'd do the same thing.
Okay, we've got our values now. Get them into Excel here. Okay. So, average, right?
And standard deviation.
Okay, so we got our average and standard deviation now. What's next?
We have to determine what our t value actually would be, our experimental t.
That's right. So let's bring this up here really quick. Looking at this equation here, remember, if we can solve for the TXP by doing this, and again, what we're looking for is to find out what, according to this data, our expected t, we think our expected t is from this data. And then we compare it to what the t-table says it probably a reasonable expected t is. And if it's greater, if our t is greater than this, then we have to reject the null hypothesis that they're the same. If it's less, then we can accept the null hypothesis that they are the same. And looking back at the question here, to evaluate the accuracy of a new analytical method, right? The analyst determines the purity of the sample, which is 100%, through these results. Okay, so if we say, yes, our method works, what would that mean in terms of null hypothesis?
You mean you're testing to see if this new method is good?
That's right.
And if it's good, then that means the null hypothesis would be confirmed, that there's no difference.
That's right. Very good. So, let's give ourselves a little bit of viewing space here. Okay, so we got our average and our standard deviation, and then we have to, where is it at? Right here. Here's our value here. We're going to take our standard deviation the actual value that we're expecting, which is what?
That's 100, right? 100%?
That's right. Because the material, they said, was 100% pure. And so we're going to take our 100 here. And, well, actually, I'm going to start off with an equal sign because this is going to be a calculation here. So I'm going to take the 100 and subtract the average. All right, there it is. Whoops. This value here is not going to be presented as a percentage. It's just going to be a number. So this needs to be 100. I'm going to change, let's see, what can I do? I guess I can make this a percentage here. Where's it at? There we go. See if that works. There we go. So there's our value. We could get more significant digits if that bothered us. Format the cell, number. Let's get just a few more significant digits here to carry. All right, so I did that part. Now what do I have to do?
Multiply it by the square root of n.
Okay, what's the n value here?
Let's see, how many times did they make the measurement? 1, 2, 3, 4, 5, 6, 7 times. So square root of 7.
All right, so I'm going to add that into here, okay? So I'm going to put these in parentheses and multiply by the square root of 7, which is, whoops, what did I do there? Put this into parentheses, get to the end here, multiply by the square root of 7, which is 7 raised to the 0.5. I like to do that as opposed to the square root function. Okay? Then divide by the standard deviation. So I can put all of that in parentheses there. And divide by my standard deviation. All right, so I got 0.9049. So what does that tell us?
Well, that's the expected t.
That's right, or the t calculated, or the t kind of apparent, right? The t experimental. So how do I compare that?
Well, you need to go to the table, and we'll compare that to what we would expect at the 95% confidence level with n minus 1, or the degrees of freedom being 6.
That's right. So I go to my table here. I get to 95% degrees of freedom 6, 2.447. All right. So for this is our t table. Okay. So our t table suspected that our n value would be 2.447, right? But we got a t calc of 0.904. So what does that mean?
Well, you didn't get it above 2.447, so the kind of the value that your standard deviation will be multiplied by in your what do you call those things?
Yeah, the confidence interval.
Yeah, the confidence interval. The value that the standard deviation will be multiplied in the confidence interval. Where's that equation?
Right here. Whoops, where's it at? Right here, right?
Yeah. The t table suggested that your value with your number of degrees of freedom should be 2.447, but we only got 0.905. So what? What does that mean?
That means we can't get rid of the null hypothesis, right?
Yeah, that means that they're probably the same.
Okay, very good. So that means that our method for measuring here is what?
It's the distribution is not different, so it's the same. So your method is working.
That's right. Very good. Because what our actual our t value, our t calculated, was compared to what our t table said it could be at the maximum for 95% confidence, we would suggest that we can't reject the null hypothesis, that our method is measuring these values as within the appropriate range of what its actual value is. Good. All right, now let's compare our answer here to our work, okay? Let's get this over a little bit. There we go. All right, so the answer here, okay, so no evidence for a significant difference between those values. We have to retain the null hypothesis, right? That's what we said. But notice how there's a slight difference here, 0.883, between our calculated value, 0.9940 here. Try to decrease the size of these cells so that we can see it all better, easier. Okay. So why the difference? Why the difference?
It looks like your standard deviation was different than theirs.
Very good. So our standard deviation here was 0.02179, and which is, well, it depends on how you, so here they used percentage, and so they used percentage standard deviation. So that wasn't terribly different, but the difference here, because we didn't use percent difference here, we used fractional difference, right? So we use fractional as standard deviation. So that's the same. But the so this should have been 0.0235, and we got 0.02179. So if you click here, you notice that the equation for this cell is stdev.p. All right. So there's lots of different standard deviations. So if I look at the list when I start writing stdev, whoops, equal sign stdev. Whoops, there we go. See all these different ways or ideas on standard deviation. Just in a kind of a reminder that statistics is not sloppy, but diverse in different ways. And this book uses mostly this STDEV down here, and that's the best one to use. I was in a hurry and I used that one, and it won't really throw this off significantly. 0.83 and 0.904 are okay, but this is probably a standard deviation for a well, I'm not sure exactly what that one is, and that would be an interesting assignment, but it kind of would frankly be less interesting in the end. If I double click here and I use that value for that way of calculating the standard deviation, you see that we get the value that they got. Okay, so that explains our difference there. All right, so moving forward now. Our variation, sorry, not our variation, but our variance, which we said was the square root of our standard deviation, right? Our variance on two sets of samples sometimes might differ significantly, or two sets of methods, right? So, for example, if I have one method for detecting something, whatever it is, my analyte, and then I have a different method of detecting the analyte, if the two methods differ in their precision, so if one has a very small variance because it's new and better, but the other one has a very large variance, then your ability to compare the two methods and determine whether or not these are different, right? The average and the mu are different, becomes a problem because that variance is an issue. And so what we need to do is we need a method for, where are we at here? We need a method for comparing variances, all right, or comparing the standard deviations. Okay, so let's think about this. We call this test for measuring differences in variations the F test. The F test is basically takes the ratio of our variance compared to another sample's variance, or if we want to compare it one to a collection of information about a known population, a well understood population, right? So when would you do that?
Like if you were in a factory and you were making something and you made it so much you know exactly what its distribution should be, and then you made some measurements and you wanted to see if your distribution matched what the known distribution should be.
Very good. Or if that would be S squared to sigma squared. But if I just had two methods and I want to compare their variance, then it would be S1 squared to S2 squared, right? But that ratio there, we can compare that ratio to an F table. And these are our critical values for our F table. And the way you use the F table is all of this is for a 95% confidence interval, or confidence level. And the ratio, again, let's see, if you have S squared of one sample to S squared of the other sample, right? This is the square of, what is S?
The standard deviation that you got from your measurements.
Right, so S squared, again, is our variance. So you put one variance above the other, and you always want to put the variance on top that is larger than the variance on the bottom so that you get a value that's greater than 1, okay? And then you look at the degrees of freedom, for the numerator and the degrees of freedom for the denominator. The degrees of freedom from the numerator, how would you get that?
Well, the degrees of freedom are the number of samples minus 1. So if you got that S squared, that standard deviation squared from A by measuring 10 samples, then it would be 9 degrees of freedom.
That's right. So if that A was on top, you go over here to 9. And then if B, let's say B had 7 measurements, then what would be the degrees of freedom?
6. So then you would look at 6 there, I guess, and go to 9.
That's right. And then 4.099 would be what you call your critical F value. All right? And then you compare that critical F value to the actual value. And let's go back to our text here. If the null hypothesis is true, if there's no difference, then the F expected should equal 1. However, because of the indeterminate errors, F expected is usually greater than 1. So a critical value is the largest value that F experimental that we can attribute to random error. Okay, so in other words, the degree of freedom is s squared, 4s squared is n minus 1, where n is the number of replicates used to determine the sample's variance, and the degrees of freedom for sigma squared is defined as infinity. So, looking at these experiments here, or this example, we have 10 samples of 10 tablets, right? And we want to determine whether there's evidence of a significant difference between the sample's variance and the expected variance. So in this case, we have an expected variance, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 9 degrees of freedom, right? We put our expected variance, 0.05, and our standard deviation, where's our standard deviation here? It's 4.3, so they gave it for us here, but that is, how would we get that, the variance for these 10 samples?
Just add them all up. Well, you take the standard deviation and then you square it.
That's right, so 4.3 is our standard deviation. And we can look at the F table for this scenario. So let's look at the F table in the hypothesis, or sorry, in the appendix 5. And again, this is going to be where we have infinity for our top and our numerator, and 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 minus 1 for our denominator. Okay, so 10 minus 1, 9 for the denominator, going out to infinity, 2.707. But that is for the one-tailed test, and we're looking for a two-tailed test here. So go back to our sample problem here. We have, again, 9 going out to infinity for a two-tailed test, because we don't know if it's going to be necessarily higher or lower, right? So 9 going out infinity for the two-tailed test, 3.333, all right? And so that's where we get our 3.333 value. And now, because our 5.8 is larger than the 3.33, what that tells us is that our variances for these two samples are larger than they would be expected to be. And because they're larger than what we would expect them to be, that means that we can use that information. That means there's a difference in the variances. We can use that information when we try to perform our significance tests. Okay, so we've introduced two things that we kind of have to know about the data to perform the appropriate significance test. One is whether it's a two-tailed or a one-tailed experiment, and the other now here is the F test, if the variances are significantly different. Okay, very good. So here's another example here where we are looking at two sets of experiments, two sets of data. One set of data, this is the penny stuff from before. One set of data here has 7 measurements and one has 5 measurements. Okay, we're provided the standard deviation already. All right, so with that, those standard deviations, all we have to do is square them. Square those standard deviations. How do we decide that the 0.051 goes on top?
You want the larger one on top always, so the value is more than 1?
That's right. For our F test, we always want a value larger than 1 there. And now we go to look for the critical test, critical value, F 6 and 4, 6 being our numerator here, right? Because that was the one, you could look back to remind yourself, but that was the one that had the 7 tests, 7 measurements, so our n value, or our degrees of freedom is 6. This one had a degrees of freedom of 4. So I'm looking for, in the numerator, 6 and the denominator 4. What do you think? Is this a one-tailed test or a two-tailed test?
You don't have any reason to think that the pennies should be heavier in one sample than the other. So you're just wondering if the two methods are different, or if the two, if the two samples are different. Anyway, so you have to do a two-tailed.
That's right. So we have to do a two-tailed test. So 6 and 4, the denominator was the 6, right?
Yeah.
And then the numerator is the 4.
Yeah, so 9.197.
Very good. So 9.197 is the max. We get 1.9, which suggests what?
That there is not a significant difference.
Let's see. That's right. There's no evidence to suggest that there's a difference, that we can't reject the null hypothesis. Again, the null hypothesis means that these are kind of the same. All right? All right. Very good. This is a good practice problem for you if you want to do it. But that's where we get our F test. After we have determined whether it's a one-tailed or a two-tailed test, and if the variances are different, then we can determine whether or not our data is what we call unpaired or paired. All right. So this is the third parameter that we need to determine or perform a test to determine whether our samples are different or not. One was, again, whether it was a one-tailed or a two-tailed. Our second was whether our variation is significant or not. That's our F test. And the third thing we need to do is determine whether our data is paired or unpaired. Here's an example of paired data. In paired data, now for these two examples, both what we're trying to do is we're trying to compare two balances in this example. So we want to compare these two balances. And one way to compare the two balances would be to collect 10 pennies and weigh each of the penny on each of the balances and compare the information that way. So we'd have two sets of 10 where they're both the same pennies, or all the same pennies. The other way, and this would be an example of a paired data. An unpaired group would be taking 5 sets of two sets of 5 pennies, right? 5 pennies each, and then weighing them on separate balances. Okay, this is an example of unpaired data. A simple test for determining whether data are paired or unpaired is to look at the size of each sample. If you have 2 different sizes of each sample, then you always know that the data must be unpaired. Does that make sense?
Yeah, because it wasn't the same data.
Very good. Or same samples to make the data.
Right.
So if the 2 samples are equal sizes, it doesn't mean that they're necessarily paired or unpaired. But if the sample sizes are definitely different, then you definitely have unpaired data. Okay, so now we get into this mess of equations, which is nice and fine, but we're not going to spend a lot of time here, okay? Because we rely on Excel. Kind of like we didn't spend a lot of time memorizing the standard deviation, we rely on Excel. Okay, so this also is an interesting paragraph here that talks a little bit about how statistics should be viewed. So in the long run here, what we want to be able to do is perform a test, which we call a t-test, and we're essentially going to compare the 2 sets of data, always going to compare 2 sets of data. Now you have been given the tools to determine whether the test is, again, one-tailed or two-tailed, whether it's similar or different variants, and then also whether or not it is a paired or unpaired data. Those are important. Those are important sets of information to go into. So this is our unpaired data statistical analysis set. Here's our paired data statistical analysis set. Okay, both of these in the end for our t-test that we perform, and that's what we call it, a t-test. Our t-test that we perform in Excel, we're looking to compare an alpha value or a p-value, right? And if it's less than 0.05, then that means your null hypothesis cannot be rejected. If it's greater than 0.05, then that means your null hypothesis, it's probably rejectable. All right, now outliers. Outliers, do you know what an outlier is?
You mean like if you have one value that is way large or way small?
That's right. So you have a set of measurements, and one of them is way too large, and it's messing up your average, and you say, oh, I got to get rid of this one. There's something wrong with it. Now you can't do that. You can't just get rid of data, right?
What if it's way bigger?
Well, we've developed what we call a Q-test, a Grubbs test, and this is even a different test which I'm less familiar with, but it's available to us to convince somebody that it was okay to throw out a data point, even after you do the Q-test and the Grubbs test or any outlier point, any test to get rid of an outlier. There will be people saying, no, you can't just do that and throw out outliers, okay? So you have to be ready for that. But this is what you would want to do to convince yourself probably that you're throwing out an outlier. In the long run, when you publish data, there's values that you would just not publish because you decided they were outliers. So others aren't going to be looking at your values so closely. So it comes down to your integrity, your concern that your own bias is messing up the measurements and the decisions of the company, right? These types of things, those types of arguments are what you're going to be up against. So here you go. These are the tools that you have available to you to make the right decisions. In the Q-test, essentially you're comparing the ratio between the gap. So let's say this is a number line that represents our different values that we measured. And this is the one that seems to be the outlier, and we want to know if we can get rid of it. We compare the gap to the range. The range being the distance from the one that's furthest away from it numerically. And this gap is the distance to the one closest to it numerically. Okay? And then we have a table for n number of measurements, right? So let's see. They don't really give us an example to use, but if your ratio is for n equals 3, here our n would be 5, right? 4, 5. So our ratio is supposed to be 0.710, 0.710. And that's the gap over the range. Okay? Now, these are, again, tests to get rid of outliers. Tests to get rid of outliers. Let's talk about when you know you can get rid of outliers, okay? The only way you can determine that, yes, it is okay to get rid of outliers if, before the results come out, you consciously, in your mind, recognize there's a problem with this run or this set of experiments. The run could have been bad because I'm not sure if I actually added that volume of material, or I'm not sure if I pushed that button when I was supposed to, or I'm not sure about something that was supposed to be standard within the experimental procedure, right? So if you already have a doubt, and then the value comes out poor, then you can get rid of that value. You don't have to run an outlier test on it at all. If the value comes back fine, then you say, I guess I did do it. I couldn't remember if I did it right, but I guess I did, and you move forward, which kind of, gives you, it's kind of like an error that might turn out favorable for you. So it's even questionable to do that. That's why some people say you should never throw out any values. You have to keep all your values. If you get a value that you don't like, you have to just run a lot more until the average actually represents that value. Normalizes that value. All right, so we're not going to delve into these too much, but those are Some pretty interesting things there. Okay, fabulous. Good job.